Professor Lijun Zhang. It's correct, because my pronunciation
yes,
is not so good.
Yes,
but I hope I will say it correct. So please, we standard 1 hour talk and the questions so on. Please, Professor Zhang.
Okay. Thank you so much. I think now, after the 2 wonderful lecture, for 2 hours long lecture, I think all the audience now are full, mentally or spiritual, but should be very hungry physically. Now, the last lecture, I suppose I wish I could give a small dessert for everyone. So first, I would like to take this opportunity to thank the organizers to give me this opportunity to to give this lecture. And to be honest, in PDE, I can say I am a student more than a lecturer, because I'm working in dynamical system method or dynamical system analysis, more in ODE, not in PDE. But the model equations we started are nonlinear wave equation. That is from the PDE. So also we can say it is very related to the PDE. And also from the 2 talks, I just, because of the time, I didn't get enough time to discuss my questions with the 2 professors. So from these 2 talks, there are some the definitions or the approach or the method they mentioned in their presentation are very, very, from the name, some of them are same in ODE, dynamical system. But, we may have some different meaning, or maybe the main idea are same, but the details or the definitions in our mind that's not so same. Still something like the Professor Wei, he mentioned the glowing method, and he mentioned outer and inner solutions. That is in dynamical system, especially recently, I'm working on singular perturbation, singular dynamical system. And that is, we also use this glowing method. And also we use outer and inner solutions. I think the main idea might be same. So I happened to get into this field. One is because the equation, model equations I'm studying is from the PDE. The background is from the PDE. And another reason is recently I'm working with Dr. Stephen Yuan from the Education University of Hong Kong. And just we discussed, he taught me Professor Wei is his lecturer when he started in his university. And from him, because now we have some cooperation, and from him I know more about the blow up and the singularities, about the solutions of the nonlinear PDEs. So from this, I've also found, especially from the first talk from the Professor Warren, I also noticed there are some ODEs, dynamical systems. I'm not sure because some of that I'm not so familiar with this. So some of that maybe they have also have the analysis, or they know the result or not. I'm not so sure. So later on, I will check their work and to say, or we may have opportunity to discuss later to say if there are some opportunity to cooperation. So here is my email if you are interested, and later on we can discuss by email, or anyway we can discuss some possible cooperations. So my talk is about the traveling wave solutions of nonlinear wave equation. So I mentioned is a method about, we call it dynamical system approach. So the outline of my presentation is like this. First, I want to introduce a little bit about the traveling wave solutions of nonlinear partial differential equation or nonlinear wave equations. Why we study traveling wave solutions. And I will mention some direct method to find the exact traveling wave solutions. And then next, after this, I will mention why from here it is necessary, or what is advantage of the method of dynamical system method to apply to study the traveling wave solutions. And then, can you hear me? Everything's fine? Okay. So next, I want to extend this method to study the traveling wave solutions and also multi-wave solutions of some higher order nonlinear wave equation. Is everything fine? Oh, sorry. Okay. And now recently we developed this method to study. We use singular perturbation theorem applied to study the traveling wave solutions of the singular perturbed nonlinear wave equations. And we will study the persistence, or after the singular perturbation, the existence of the traveling wave solutions. And the last, maybe the last two, I will leave to Friday lecture. And so today I'm going to introduce the first three part, and if there's time, I will get a little bit get into the traveling wave solution and the multi-wave of the high order nonlinear wave equations. Okay, first, let's say the traveling wave solutions. We know the traveling wave solution is a special kind of exact solutions of the nonlinear PDEs, especially for nonlinear wave equations. This solution is very important because this solution is we say it is characterized as solutions which are invariant with respect to translation in space. And it is normally used to describe the process of transmission. So when we mention the traveling wave solutions, we have to mention the first observation from John Scott Russell. So in 1834, in 19th century, he observed from a canal. He observed this solitary wave, and this wave is motivated by a boat carried by the horse. And he noticed when the wave, the water before the boat, after the boat stop, but the wave keeps the same shape moving. After long distance, it disappeared in the sea. When he just discovered this, it is not convinced for the researchers, and he tried to do the experiment in his lab for many times, but unfortunately he couldn't find it in the lab at that time. And now for this solitary wave, he observed it is do the experiment later on in Harvard University. And the wave, this is motivated, the solitary wave motivated by this boat. When the boat stop, and this wave keeps the same shape and travel for a long time. Why it is not convinced or believed by most of the researchers, because they think this is can't keep keeps because this system is not conserved, so shouldn't be conserved in the same shape to keep the energy. Fortunately, till 1895, a Dutch mathematician, Kantwerk, and his students, de Varus, proposed a partial differential equation that is a KdV equation. The KdV equation, it is one simple version of the KdV equation is given by this. And for this equation, it's not difficult to find the exact analytic solutions. The solutions is given by a hyperbolic second equation. And the graph or the portrait of these solutions looks like this. And from the shape, we will know these solutions looks like the soliton observed by John Scott Russell. So this is about the traveling wave solutions. So how to find the exact solution, or how to analysis by the mathematics, the rigorous analysis to study the traveling wave solutions is also very important. So this is the background of the traveling wave solutions, and recently a lot of methods are developed to study the traveling wave solutions of nonlinear partial differential equations. And the basic main idea of this method is a direct method I mentioned here. It is for nonlinear partial differential equations. Take some ansatz, or assuming the solutions having some special forms or some special properties. And then the nonlinear partial differential equations can be transformed into the nonlinear algebraic equations. For this step, how to do this ansatz, sometimes the method they use, they just suppose the solutions can be expressed by the linear cooperation or the algebraic, the polynomial form of the function of some exponential function, like exponential function, or second functions, or sine, cosine, or the so-called curved elliptic functions. And we get this method and some like the F expansion method, extended F expansion method, or some like this solution, assuming they have some they suppose they have some properties, like they solve these solutions by some solvable simpler equations, like the Riccati equations, linear equations, or the so-called G-touch over G expansion method are proposed. And thousands of papers are published in this field to reduce this partial, the PDE, nonlinear PDE, to algebraic equations. Of course, we know even for nonlinear algebraic equations, it's not easy to find the solutions. Luckily, with the development of the symbolic computations, for these nonlinear algebraic equations, there are a lot of softwares like Maple Mathematics or MATLAB, and all these softwares can do the good symbolic computations and to get the solution of these algebraic equations. After get the solutions of these nonlinear algebraic equations, then they can get the solutions of the exact solution of the nonlinear partial differential equation. That's the basic idea of this kind of work about the direct method. But unfortunately, in this work, there are some errors happens, some mistakes happened in these works. And in 2009, the Russian mathematician Kudryashov, he wrote a paper. The paper published here, he gives the name is the 7 common errors in finding exact solution of nonlinear differential equations. And later on the next year, the two professors, one from Australia and this from Ukraine, he gives the solutions, the same journal, Communication, Nonlinear Science, Numerical Simulation. He published another paper. The paper named the more common errors in finding exact solution of nonlinear partial differential equation. He mentioned this paper is named part 1, but I didn't say, unfortunately, I didn't find the next part 2. But in this work, they mentioned these common errors. Here, I want to show the papers here. They mention these common errors. Because still right now, a lot of work still published about this method to find the exact solutions of nonlinear PDEs. Now here the contents here. He mentioned the 7 common errors. The first errors he mentioned that some authors use equivalent method to find exact solutions, and by the equivalent method, they get the exact solutions in different form, but in fact, they are the same solutions. And the second error he mentioned, don't use non-general solution of ordinary differential equations. They just use some special particular solutions, and they announce to get the solutions. But if they use a general solution, definitely they will get more solutions, or they can get more general solutions. And the fourth error he mentioned, omit arbitrary constants after integration of the equations. If the authors do this, then obviously a lot of solutions are missed. The next one he mentioned, don't take arbitrary constant into consideration. They just take this constants to be arbitrary constant to be one. They just started one case or some particular case. The sixth one he mentioned, the fifth one he mentioned, don't simplify the solutions, and they just present the solution in a very complicated way, and it's not impossible, or it's not easy to say to check if the solutions are new or not. Even some authors, they don't check their solutions and to give the wrong solutions even. And also some authors, they include additional arbitrary constants into the solutions, and they didn't give the analysis. They just include the additional arbitrary constants into the solutions. So this paper, if you are interested in this topic, you can check these papers. And the second one I just mentioned is here. Now, I think he more focus on the common errors, not traveling wave solutions, or the solutions causing the similarity or linearizability of differential equations. And he shows the exact solutions were contrasted in these papers only for equations which are introduced by point transformations, especially to the standard KdV equation or the MKdV equations. And these are the two papers I would like to mention. If you do the exact solutions of a traveling wave solution of nonlinear PDE, you should be very careful to buy this method. And because when we started the the traveling wave of PDE, because we need to introduce extra parameter. The parameter is the wave speed. The wave speed, normally it is an arbitrary constant. The existence of the traveling wave solutions, all the properties of these solutions normally depend on the wave speed. all even in the equations, in the nonlinear partial differential equations, they involve some parameters. The parameters, you know, it's not exact value. You have to do the analysis. That's very important. Now, next, let's say what is the main idea of the dynamical system method to study traveling wave solutions, and why the dynamical system method can be applied to study the traveling wave solutions. You know, when we considering the traveling wave solutions, that means for a nonlinear partial differential equation. Here, I just mentioned like it is 1 + 1 dimension partial differential equation or wave equations. Of course, it is in n+1 equation, still the same framework. In the framework of the traveling wave, the partial differential equations can be transformed into the nonlinear ordinary differential equations. Here, the extra parameters just I mentioned here in 1 + 1, this is C, we call it wave speed. If it is n+1, extra n-1 parameter will introduced here. So when we get the ordinary differential equation, we have the parameters. So if we do the analysis, we need to study the parameters, the bifurcations, the qualitative analysis, and to study the solutions of the ordinary differential equation. More important is the traveling wave solutions of nonlinear partial differential equation. Mostly it care for the traveling wave solutions. More important solution, it is called solitary wave solution, kink, anti-kink, or periodic wave. Of course, there are some other different kind of traveling wave solutions, like later on I will introduce. So we call it singularity, but this singularity we mentioned here from the partial differential equation, we means this solution, this traveling wave solution has some singularity. That means it's not a classical solution. It's not a small solution. It has some at some point or some and some straight line, some domain, or some range. This solution are not smooth. Normally, it is a point or along a straight line. And I'm not sure if this singularity is same as a singularity means in a PDE, but I will check and to study if they are same by the definition. And this definition, this is a singularity we called is from the ODE. From the orbits, we know traveling wave solutions, they have very good, after this transformation, the solutions between the PDE and the ODE, they have very good correspondence. The one is the solitary wave solutions concerned in PDE or nonlinear wave equations. It corresponding to the harmonic orbit of the dynamical system or ordinary differential equation. And kink, anti-kink is normally corresponding to heteroclinic orbit, and the periodic wave corresponding to the periodic wave. If they have this good cooperation, then correspondence, then we have the corresponding relationship, and then we can study the cared or the concerned traveling wave solutions by studying the bounded orbit of the nonlinear ODEs or dynamical systems. From this point of view, we just study the harmonic orbit, heterodic orbit, or periodic orbit. So this is the main idea of this method. And first, so I want to mention some pioneer work of this method introduced. I think before I introduce the first work is this Professor Dai Huihui. He is from Hong Kong City University. Unfortunately, he passed away when he was very young, a couple of years ago. And Professor Dai Huihui and Professor Zhao, he first introduced this method. He introduced this method to study model equations to study the wave traveled along a rod, elastic rod, and they find this method. They apply this method to this equation, and later on, the Professor Jibing Li, when he visited Professor Dai Huihui, and Professor Jibing Li now he is working in dynamical system and differential equations, ordinary differential equations for many years, and he knows the dynamical analysis very well. So when he observed that, he noticed that this method can be applied for the study of the traveling wave solutions for different kind of partial differential equations. And at that time, I was studying my master's with Professor Jibing Li in Kunming University of Science and Technology, and from 1999 to 2002. At that time, I started to learn this method and apply this method to study the traveling wave solutions. This is the first we applied, and later on, Professor Jibing Li published I think 3 books on this method about how to apply the dynamical system to study traveling wave solutions. Here's some work, and I would like to show the 2 books here. First, the 2 books he mentioned, he applied this method to study the different kind of nonlinear wave equations, the traveling wave solutions, by the bifurcation, exact solutions, and also I think this book published in 2013. If I'm not wrong, in 2009, he and Professor Jibing Li and Professor Dai Huihui, they published the first book on this method. Unfortunately, now I couldn't find the picture for this book, and in 2019, Professor Jibing Li published another book. The book is named Bifurcation, Exact Solution in Invariant Manifold for Nonlinear Wave Equations. He extended to this dynamical system method to study some high-order differential equations by finding or reduce this equation to invariant manifold. And maybe I will introduce this later, maybe in next lecture. Okay, so next let me move on to more details about this method. For the dynamical system method to study the traveling wave, I just have mentioned in the traveling wave framework, or after the transformation, the traveling wave will introduce the new variable, and then the partial differential equation is reduced to ordinary differential equation. And if this system can be reduced to the second order nonlinear differential equation, ordinary differential equation, of course, then this system we can write in a planar dynamical system. Of course, here we need to do some reduction. Normally, the equation is high order. Sometimes we can do some like the integration to reduce. If luckily we can reduce to planar dynamical system, then we can use this method. Or we can say, luckily, there are a lot of partial important traveling waves, important nonlinear wave equations, they can reduce to the planar dynamical system. And then we can write this equation to in planar dynamic system. And then but remember here, we introduce some actual parameter. The parameter is the wave speed. And also maybe some parameter, extra parameter involved in the equation. So we have to study the bifurcations, to study in the different bifurcation set of the wave speed and other parameters, the qualitative analysis, the phase portrait of this dynamical planar dynamical system. We need to know. If we know, like here, I just show some of this phase portrait, like the planar dynamical system portrait here in the first graph here. We know this if this system has a saddle and two center, and this is if it is a Hamiltonian system, here it is integrable or Hamiltonian system, then we will know the orbit, the phase portrait in this way. In some bifurcation set, the graph maybe like the phase portrait may like this, and it might be for some parameters in some region of the parameters, it can be have two center and one center, and it have this orbit, we call it heteronic orbit, and this orbit we call it harmonic orbit, and also some periodic orbit, and it also have this opportunity, or it might be in this form. Of course, these graphs are from some concrete model equations, and I will show the papers later on. And if we can find this, and by the corresponding relationship, the relationship between the nonlinear, the traveling wave solution of PDE and the orbit, and we will know here clearly we can say, for this orbit, the periodic orbit is corresponding to the periodic traveling wave solutions. And for this harmonic orbit, it is corresponding to the solitary wave solution in a peak form. And this one, it is a harmonic orbit. It's corresponding to the solitary wave in a valley form. Or we say it is in soliton, sometimes they call it bright soliton, and this one is called dark soliton. And for this orbit, the head orbit, it's corresponding to a kink wave. The kink wave, it is with the time, it is goes to a bounded value. Here it shows like for this orbit, if it goes to the equilibrium point is -1 and 1, 0, then with the time increase to the positive infinite, it goes to 1. And in the negative side, it goes to -1. And it is increase like this wave is called kink. And this one, the below one, it is a lower one, it is corresponding to kink, anti-kink. This is a relation. So by this relation, if we can give, we only need to do the analysis of the bifurcation and qualitative analysis, then we can get the various traveling wave solutions. And now this graphs is from for the bifurcations here. I just want to show the papers here. And now this is a very this is the generalized PC equation. For this equation, you know, the first we introduce a traveling wave. The new variable C is x minus ct, and we can reduce this generalized CP equation into a second order differential equation. For this equation, this equation we can we know it's easily, it is corresponding or it is equivalent to a planar dynamical system. And for this system is a Hamiltonian system, and it is a conserved and integrable system. So we do the analysis here. More parameters involved. One is from the wave speed, and another one is from the integration. The constant of integration, just like I mentioned, Khrushchev, he mentioned if you ignore this constant of integration, then definitely some cases, a lot of cases will be ignored and missed. And here, for these two parameters, after some reduction, we do the analysis, bifurcation analysis, and we know in different range of these parameters, and we can get the bifurcation. Here is a bifurcation set and face portrait of this system. Here, you know, we have the different cases, just like I mentioned there in the graph. And it is also in this case, the parameter if in this case, and also this case, it is related to the wave speed. So the wave speed, if it satisfies this condition, the phase portrait, the bifurcation set and the phase portrait will look like this. And so from this one, we can say clearly to observe the various the different kind of traveling wave solutions of this PDE. This is a basic idea. So I want to show the details. If you are interested, you can read the papers. I just want to mention here. Okay, this is the first we use it to study for the planar dynamical system, and it is also an integrable system or Hamiltonian system. And the next case I want to mention is if this system is not a non-integrable system. Some of this system is not integrable system. Then similarly, we can do the bifurcation analysis. Of course, it's not that easy. Because when we want to find the bounded orbit, first we need to analyze the equilibrium point of this system, and also more important, we need to study the bounded orbit. The bounded orbit here in the non-integrable system, maybe we need to find here, like here for this example, like KdV-Burgers equation. It has for the system, it has a saddle point, and two here is two forks. If it has this equilibrium point and the orbit, you have to do the qualitative analysis and the bifurcation. For some cases, the phase portrait may look like this, and for this one, the solutions will all. It will goes to like we say this orbit for this the boundary orbit, it is goes to the stable manifold of the equilibrium point, and the unstable side it is goes to the forks. And then for these solutions corresponding to the traveling wave solutions, it will looks like it is oscillate solution, but the amplitude will gradually reduce in the negative side, time side, and goes to here if they go to some fixed value of this system. And also, you know, for some parameter, for some bifurcation set, the orbit, it may looks like this. There's a saddle, and this is this might be a node saddle. We need to find the heterogeneous orbit connected to the two equilibrium point. If we can find it, then for this orbit, it's corresponding to a kink. And the kink might be increasing or decreasing, or it might be oscillate also, but in the positive in the infinite time, it must go to the fixed value. This is a system for the non-integrable system. So now next, let's say for this planar dynamical system, how it related to singular traveling wave. The singular traveling wave is sometimes when we study the corresponding dynamical system, this system has singularity. This singularity, I mean, this function g is not a continuous function. It has singularity here. If u can be 0, then the singularity appear here. Now we started the two cases, and Professor Jibinli named these two different cases to be first class nonlinear wave equation and the second class nonlinear wave equations. The first class nonlinear wave equation, that is the denominator here, u is not related to y. The partial derivative with respect to y is 0. That means here only x involved in this function. This is called first class nonlinear wave solutions. And the second class is the denominator here, y is involved here. Why it is classified the two classes? Because we observed that for the first class nonlinear wave, for the first class and the second class, we notice the nonlinear wave equations, the traveling wave solutions, they have the we can say they have a different the weak solution or singular traveling wave, the singular traveling wave solutions. Now let me show the first class nonlinear wave equations. The first class nonlinear wave equations, of course, there are a lot of different, for different equations, they have this similar, or they have this phenomena, that is the corresponding dynamical system is with the singularity. The singularity here, we can say from the denominator here, for this equation, the gamma alpha squared c is the wave speed. Gamma alpha is from this equation is from the generalized Kama's-Holm equation. That's a very important equation in nonlinear wave to describe the shallow wave, the traveling of the shallow wave. And the parameters c0 alpha gamma is from the equation, from the original equation. And c is a wave speed. And the denominator here, we know the denominator is zero because it's linear in phi. So we have a singular line. The singular line, that is phi equals to gamma plus r squared over c, alpha squared times c over alpha squared. When phi equals this value, then the singularity appear, because the denominator becomes 0. The singularity appears here. And after some, we introduce time rescaling of this equation, because this is a non-analytic system. It's not easy to start. After introduce time scale rescaling, we introduce this system into a analytical planar system. And for this system, we will find the two different systems, they have the same topologic phase portrait, but the difference only appears in this singular line, In this singular line, for the first system, it's not well defined, but for the analytic system, that's a singular solution. So for the phase portrait here, I just gave the example here is from the Kama's-Holm, the generalized Kama's-Holm equation, and also after the transformations, it is we mode this singular line phi to some some values. I just mentioned this value to is 0. We just do transformation, then we can do it easily. And here I use this line phi equals 0. This singular, we suppose it's a single line without loss of the generalization. So we know we have this singular line, and in the different bifurcation set, we have the face portrait. It looks like this. And now we have do the analysis of the planar dynamic system, but more important, we need to return this result. Go from this result, we need to go back to the traveling wave solutions of the partial differential equation. And for the phase, the trajectory of the orbits which are not connected or with a single line, no any problem. Like here, the periodic orbit, it's corresponding to the periodic traveling wave solutions. And here, if we have, like in this case, there is a harmonic orbit, no problem. And this harmonic orbit is corresponding to a solitary wave. But what happened to this orbit? It is intersect with this singular line, And here we can say along this line, there's for this case, this is a straight line. We get a triangle. In this triangle, all the orbits are periodic orbit, but for this we know they are all correspond to the traveling wave, periodic traveling wave. But for this triangle, what the traveling wave solutions they should correspond to? Here we know along this orbit, the direction here is to the right side, to the infinite, positive infinite, it goes to this sandal. And another side, it goes to this straight line, and we have plot infinite time along this orbit. If we along this orbit, the motion goes to this point. This is a singular point, infinite time. And here also for this orbit, it is inverse in negative infinite. It goes to this single this, because this is corresponding to an unstable manifold of this sandal. So for the positive finite time, it is goes to this value. But we will observe for they goes to the same value. Here is phi equals 0, infinite time. Of course, these two orbits, this triangle can be a limit of this family of this periodic orbit. And so there are two ways to explain what this triangle, what the traveling wave solutions is corresponding to. One is by the periodic, the limit of this periodic orbit. And another way is we also can explain it by the parameter, the bifurcation, with the parameter going with increase or decrease. For this case, it might be with the change of this parameter, this orbit, and for this case, sorry, the third one. For the third one, this orbit, the limit can be, this is a harmonic orbit, we know, with the increase or with the change of this variable, and we will know this orbit will approaches to this case. So it can be a limit of a family of periodic wave, or it can be a limit of the family of harmonic orbit, with this limit with respect to the parameter, and this one is with another parameter. It might be related to the equation, the different parameter, but we get the same limit. And it has been proved that for this kind of case, this solution corresponding to a weak solution or the singular traveling wave solutions, it is called Pekin. This solution, it is corresponding to a Pekin. And the Pekin, what's the difference between the Pekin and the smooth solid wave solutions? The difference is the solutions, the Pekin is smooth, is continuous but not smooth. They have a jump in their first order derivative. They have a jump at this point. When they reach this point, they have a singularity at this point. Of course, these solutions also can be proved because it is the first proved by the physicists. They find the Pekin really exist, and from here we observed it is corresponding to the singular trajectories. So for other partial differential equations, we also observed this case, and so it can be proved more general for this case. All this orbit intersect with this horizontal, this vertical singular line is corresponding to the solutions, the Pekin, all the Pekin solutions here. And the papers here, if you are interested in, I just want to show you the papers I mentioned here. It is in this patient. This is published in 2006 about this generalized Kamath-Holm equation. This Pekin, for this equation, the Pekin solutions, they find it is in this form. It is exact solutions, and these solutions, they mention all the first discovered is in this form. Actually, from our analysis, we know this Pekins may not in this form. It can be in other form. Also, it can generalize to other forms of this Pekin. So here is a graph of these functions. I want to show the details. I just show the graphs of this, and we know now we know it well. Here in this case, it is corresponding to a Pekin, and the Pekin solutions here, and these are periodic wave solutions. And for this one, it is corresponding to solutions, because the solution, when it goes into close, very close to the singular line, it moves very quick from the upper side goes to the lower side, and along the limit of this family of periodic wave, it goes to this point and jump to this point, and then go into another circle. So this corresponding to a periodic Pekin solutions. So if we get this solution, this is the singular line or vertical line. That is, I just mentioned the first class of solutions that corresponding to this solution. So that is the merit or the advantage of the dynamical system to study the traveling wave solutions. We don't need to find the exact solution. By the qualitative analysis and bifurcation analysis, we know how to find the Pekin. And even later on, I will mention another kind of the weak solution or the non-smooth solution. It's called Kinken or compactant, this kind of solutions. Okay, this is for the vertical singular line, the first class of traveling, the nonlinear wave equations. Next, let's see. I think I have a couple of minutes to mention the second class of nonlinear wave equations. Here, I give the example is the work I published in 2013. It is called nonlinear Klein-Gordon model equations. And these equations here, it is proposed when do this chain model of particles with identical mass, and it is observed these solutions has these weak solutions, and it is goes to not like Kinkin. The Kinkin reach, they just approximate to or tends to a limit of some fixed values, the two sides, positive or negative, infinite time. But for these model equations, and in this lab, they do the physical experiment. They observed this solution. This solution reach these values in finite time, not in infinite time. Here, mathematically, we write the solution that here, like it is the solution arrive. Of course, here we do the rescaling. It is not the real value of this model equation. It is arrives to 1 or -1 in finite time. Oh, sorry, 1 and -1. Yes, 1 to -1 in finite time. Not like the kink. And these solutions, this traveling wave, it is called Kinkin by the physicists. So first they gave this name. And how can we observe these solutions? What they corresponding to the solutions of the dynamical system? So for these model equations, after the reduction I want to mention, it is reduced to this equation. And the singularity here, appears y equals, it might be 1 or 2 singularities. Here, for some cases, it has 2. For some cases, I did some simplify reductions here to a very looks like much comfortable for our mathematics, and reduce to this equation, and we get the bifurcations and the phase portrait of this equation, and we get the singular line are horizontal straight line, and we notice a lot of orbit, they intersect with this singular line. And what kind of the solutions is corresponding to the traveling wave solutions? And that's to study these solutions are critical. And what the Kinkin solutions they observed in the lab corresponding to the solutions here. Now I just, because due to the limited time, I just gave one example to show the singular line here. In one case, they have the two singular line, they combine into one. They merge to one. And for this singular line, for this case, and we will find for this equation, we start this equation, and we find they reach this singular line in finite time, not in infinite time. That is also, if I'm not wrong, it is a blow up. It's a blow up phenomenon. Of course, blow up in qualitative analysis, there's another blow up technique. That's another totally different meaning of this blow up. But this blow up, just if I'm not wrong, that is the reach some values, the derivative of the value reach infinite. Here it is a derivative arrive. The derivative disappear. For this point, they have the singularity here. The second order derivative approaches to infinite. That is the blow up. The meaning of the blow up for this case, and for these equations, likely we can get the exact solutions. The exact solutions by this equation we observed. We gave the solution, and also it can be shown. This is a weak solution of this PDE. This is kinken or anti-kinken. It depends on the shape of these solutions. So we give the exact solution. So we notice the difference between the horizontal or vertical straight line. The orbits, they have the different phenomena. So that is why we classify this equation to the first class and the second class. I think time's up. Now I want to stop here. And next lecture, I would like to introduce about the multi-wave and how to study the high order differential equations and the singular perturbations. Okay, thank you so much for your time, for your patience.
Thank you very much. Really very interesting, lecture. Professor Lijun, what maybe it's full question. But in Hammasa whole equation, how you obtain this system of two equation from Hammasa Common equation, which is of third order? What I did not understand what the connection between this system.
The Hammasa-Common equations. I think it's I just want to introduce the method. So let me show you the Hammasa-Common equation. This one, we reduce it like after the reduction. Here, we know after the reduction, this equation can be, it is a third order. The original one is a third order differential equation. Yes. And this equation, luckily, can be integration, reduction by integration.
Not so simple. It is it is not possible to show simple how to obtain this ordinary system. Yes.
Yeah. Here, for this one, luckily, we reduce to second order. So the planar dynamical system analysis works, but extra constant time integration is introduced. So we need to do the bifurcation very careful to get a different kind of cases. But the next lecture, I will show you.
Maybe it is not now. It is difficult to say, but really, for me, it would be interesting to understand it really. So maybe for next lecture, I get that at next lecture it will become more clear for me.
Yes.
Thank you. So question, please. I propose not only me, but I get it. Somebody from our audience would like to ask. Please, question. Have a question? Whether we have question, I try to examine all our list. No, nobody gave some question in written form, but maybe somebody would like to
raise your hand.
No question. No question. No. So now I would like to tomorrow next time on the second lecture we will be more we will be formulating more questions, I guess. So thank you very much. It was very interesting.
If you have questions you want to discuss, so you can email me, and maybe we can find some way to discuss.
In any case, I will ask you to send us this your presentation after the
second
lecture.
I will after I finish all
after second lecture. But
yes,
maybe Professor Rozanova would like to ask somebody, a specialist in this technique.
Okay, please.
Yes.
Тогда Розановой надо микрофон включить.
Ольга, Professor Rozanova, do you like to ask something? He is also in our audience.
I guess most of the audience are Russian here.
Yes,
I only know how to say здравствуйте.
We try to
Ольга Сергеевна, ваш микрофон можно включить. Вот.
Yes, thank you very much, Lijun, for the very interesting talk.
And Olga, thank you so much. Thank you so much. I just forgot to mention Professor Olga. she introduced me to this international school. Thank you.
Whether you can do some question or some explanation.
No. It's all clear for me because I'm familiar with this subject. Thank you very much. It was very clear.
No, maybe later we will ask you, and you will also to do some comments to such a lecture, because very intensive, very many information, very complicated subject, very many notions introduced.
Introductory lecture.
Yes. No,
Yeah,
I guess that Olga Rozna will help us to understand more detail. Yes.
I want to take a half more minutes to mention is I'm really very happy. Just as I said, I'm a student in PDE, and still something I'm not so clear. And also, today from the two talks. From these two talks, I learned a lot, and I try to combine some definitions like these singularities with compare the difference and the same compare these definitions with the dynamical system with ODE, and this might be very helpful for me, especially for me.
Yeah, very fruitful approach. Yes, of course, it is very interesting. Really, I would like to do some effort to understand more detail the subject. Thank you very much. Thank you very much. Very much. Very many thanks. Very many. So, if somebody would like to ask to do some comments, yes, not. I don't see any wishes. So, if nobody would like to say, then we have to finish today's session, and we will meet for tomorrow's interesting continuation of our session, of our conference. So, thank you very much for all our audience for attending in this meeting in general. In my opinion, it's a very interesting meeting, and I hope for continuation and interesting discussion in the next days. So thank you very much, all our people who are here now.
Thank you. Bye.
Lijun, thank you very much. Thank you very much. Thank
you. Bye, Olga.
Bye. Thank you very much.
Bye.
Bye.